Hi guys, you're welcome to my channel. Today we want to talk about the electromagnetic spectrum, and the concept I will be focusing the lecture on is the concept of the visible light. When you talk about the electromagnetic spectrum, like I explained during our wave class, I said electromagnetic spectrums is the arrangement of the electromagnetic radiations in order of their increase in frequency and decrease in wavelength. So when you look at the electromagnetic radiations, we have reverse G, though I omit one here, and that is the microwave. So just let's focus on this. When you talk about these electromagnetic radiations, from radio wave, infrared, visible light, ultraviolet, X-ray, and gamma ray, as they move to this end, we have the frequency increasing and the wavelength decreasing. But radio wave is not visible to human eye because of its wavelength. Likewise, the infrared. The only part of the spectrum that the human eye can comprehend is within 400 nanometer to 700 nanometer. This is the wavelength that the human eye can comprehend, that can see, and that is the range of the visible light. Are we together now? Now, taking this visible light into consideration, we have that in visible light, there are colors like red, orange, yellow, green, blue, indigo, and violet. The way they highlight these are the all colors that we have within the visible light spectrum. And that is why we are going to focus our class on this color. We are going to talk about the frequency of their photons, and we talk about the wavelength of their photons, likewise the energy of their photons. Now, as we move towards this end, their frequency increase. There is an increase in frequency. And whenever there is an increase in frequency for a photon, there will be an increase in energy. But frequency is inversely proportional to wavelength. Are we together now? Therefore, as the frequency increases towards these ends, the wavelength will decrease. Likewise, when you move backward like this, the wavelength is said to increase like this. So if you consider this direction, the wavelength will be increasing, while the frequency tends to reduce and the energy will also reduce. In a nutshell, red light has the highest wavelength, but the shortest frequency and the lowest energy. Followed by orange. It has the highest wavelength, followed by red. And its frequency is also small, but greater than that of red light. And the energy is also greater than that of the red light. So as you move from orange to yellow, the frequency is increasing and the energy is also increasing. On getting to blue, when you get to blue, blue has a very high frequency compared to red, orange, yellow, and green. And if you have watched my lecture where I explain the reason why the sky appears blue, you see that whenever a body has a very high frequency, the body tends to oscillate more. A body that oscillates more tends to scatter more. And that is one of the reasons why you see blue dominating the sky. Then indigo and violet. Okay, so if we are talking about the frequency of photon between yellow and blue, which of these two photons has the highest frequency? You should know that it is blue. If I said between orange and green, which has what? Highest wavelength. You should know that it's going to be orange. Are we together? So with this now, we can know which we have highest wavelength and which we have what? Low frequency. Now, there is need for us to understand the range of their wavelength and the range of their frequency. Why? Because in most cases, examiner might ask us that which of the following visible light spectrum colors is corresponding to this certain wavelength. There is need for us to give response to that question. Now, we understand that it ranges from 400 nanometer, that is the wavelength, to 700 nanometer. So I would like to rewrite it in order of their increase in wavelength for better understanding. You know, this is the order of their increase in frequency. Now, if I write it as V, I, B, G, Y, O, and R. This is how, okay, I think I need to position this well. So I have V, I, B, G, Y, O, and R. The way they have like this is how their frequency increase. Now, visit for the violet. The wavelength of violet is within 400 nanometer to approximately 425 nanometer. Are we together? And for that of indigo, from 425 nanometer to 450 nanometer. Are we together? Then for blue light, from 450 nanometer to 500 nanometer. Are we together? Then for the green light, from 500 nanometer to 570. 570 nanometer. Then for yellow light, from 570 nanometer to 590 nanometer. Then for orange, from 590 nanometer to 620 nanometer. Then our red light range from 620 nanometer to 700 nanometer. Do we get this now? Now, if I throw a question like, which of the photon is corresponding to a wavelength of 530 nanometer? So we come to check our spectrum. We see that green light is what is corresponding to that wavelength because it's within 500 nanometer to 570 nanometer. So if I ask which of the wavelength is corresponding to, let's say, 650 nanometer, so we should know that we are talking about red color. So if I say which one is corresponding to 430 nanometer, we are talking about the indigo because it ranges from 425 to 450. And this is how to answer questions when we are talking about corresponding photon to a certain wavelength. Do we get this now? Now, let's quickly talk about their frequency. How do we calculate for the frequency of a photon? The frequency of a photon is given as the Planck constant multiplied by frequency. The energy of a photon, sorry, I want to talk about the frequency first. Remember, velocity is equal to wavelength multiplied by frequency. If the velocity equal wavelength multiplied by frequency, for a photon, we talk about the speed of light. And the speed of light in vacuum is about 3 times 10 raised to power 8 meter per second in vacuum. But if you have it in another medium other from what? Other than air or vacuum, we talk about the speed of light equal the speed of light in vacuum divided by the refractive index of that medium. Are we there? That is, you cannot say that the speed of light is constant because it changes in every medium. So, aside from vacuum or air, the speed of light is going to be the speed of light in vacuum divided by refractive index. Now, let's take for instance that the speed of light in water. The refractive index of water is about 1.33. The speed of light in glass, the refractive index of a glass is about 1.5. So I can say the speed of light in water is going to be 3 times 10 raised to power 8 divided by 1.33. So, and that will give us 3 divided by 1.33. Okay, so the speed of light in water is about 2.25. Okay, let me just say 2.26 multiplied by 10 raised to power 8 meter per second. You see now that it's quite small compared to the speed of light in air or vacuum. Also, if I have a refractive index of 1.5, I will have that the speed of light is 3 multiplied by 10 raised to power 8 divided by 1.5. So, and that will give us 2 times 10 raised to power 8 meter per second. Now, I want you to understand something here now. If you look at the speed of light in glass, it's quite small compared to the speed of light in water. This is to tell you that the speed of light will reduce according to what increase in refractive index of that particular medium. When you have a medium with a very high refractive index, the speed of light is said to be what? Very, very small in that medium. Having to understand that, let's come back to know the frequency of the given photons here. Okay, so we said that velocity is given as lambda multiplied by frequency. Now let us pick a wavelength of 450 nanometer. I can decide to pick 500. You can decide to pick what? 590, your choice. So I want to consider indigo, and you can decide to consider the blue light. Another person can decide to consider the green light. We are not to look for the frequency of all of these, and if you have a chance, you can do that for fun. So if I have a wavelength of 450 nanometer, and I want to find the corresponding frequency to that, I will say the speed of light, since all of them, all of these now, they have equal speed, and that is the speed of light. The same thing goes to the electromagnetic radiations. They also have the same speed. What is different about them is their wavelength and their frequency. Now, let us find the frequency corresponding to 450 nanometer. I would like to know that the C is 3 times 10 to the power of 8 meter per second. Note that. And at the same time, you should know that 1 nanometer is equivalent to 1 times 10 to the power of -9 meter. Do we get this now? So if we get this now, we can now say frequency is equal to the speed of light divided by lambda, and that will be 3 multiplied by 10 to the power of 8 divided by 450 nanometer is the same thing as saying 45 multiplied by 10 to the power of -9. Are we together now? So that is 450 multiplied by -9. So we have that F is 3 multiplied by 10 raised to the power 8 divided by 4.5 multiplied by 10 raised to the power -7. So if this should be the case now, we can say 3 divided by 4.5 multiplied by 10 raised to the power 8 plus 7. So what would that give us? 3 divided by 4.5. So we have F equal 6.67 multiplied by 10 raised to the power of, this will give us 15, so that will be 14 hertz. Now, the there's something I would like us to understand here. So if I have a wavelength of 450 nanometer, the corresponding frequency will be 6.67 multiplied by 10 raised to power 14 hertz. Now, because of the definition of frequency, what is the definition of frequency? Frequency is defined as the number of cycles per second. So the number of cycles per second, it means the unit of frequency that we call hertz can also be equivalent to per second. So you can say frequency is measured in per second. If that should be the case, we'll come back to the use of this later. Now we've determined what? The corresponding frequency. Now let us now determine the corresponding energy to this particular wavelength. Are we together now? So how do we go about that? So for us to know that, we just understand that energy is equal to the Planck constant multiplied by frequency. Planck constant multiplied by frequency will give us the energy of the photon. And Planck constant is equivalent to 6.6 multiplied by 10 raised to power minus 34 joules seconds, if I'm not mistaken. Okay? Yeah, 6.6 times 10 raised to power minus 34 joules seconds. This is our Planck constant. Now, if this is the case, let us find the energy that is corresponding to a wavelength of 450 nanometer, and that is going to be the Planck constant 6.6 times 10 raised to power 10 raised to power, okay, then multiplied by our frequency is going to be 6.67 multiplied by 10 to the power of 14. Okay, let me include the unit of this, and that is joules second, and this one, instead of me using hertz, I will use per second, so that we can see how to get the unit for energy. Second, we cancelled second. Then I will have that the energy is equal to 6.6 multiplied by 6.67 times 10 raised to power minus 34 plus 14. Do we get this now? So the energy is therefore equal 6.6 multiplied by 6.67. Okay, so I have 44.022 multiplied by 10 to the power of so minus 34 plus 14, that should give us minus 20. Are we there? So it's going to be in joules, since seconds has cancelled second. So this is equivalent to 4.4 multiplied by 10 to the power of minus 19 joules. Now if you consider this, you will see that this value is very, very small. And this is one of the reasons why the energy of photon is not expressed as joules. Because if you express it as joules, it's very, very small. Then, for us to write it maturely, we have to convert this to electron volts. Now, what is the equivalent of 1 electron volt? So I have that 1 electron volt is 1.6 multiplied by 1 electron volt is 1.6 multiplied by 10 raised to power minus 19 joules. Are we there? So this is the relation. Now watch something here. I want you to see something. If I will convert from electron volts to joules, I will be multiplying by, if I want to convert from joules to electron volts rather, I will have 1 electron volt divided by 1.6 multiplied by 10 to the power of minus 19. This is what I will multiply with. And if I'm converting from electron volts to joules, I will have 1.6 multiplied by 10 raised to the power minus 19 divided by 1 electron volt. That is what you multiply with. Though I will be making video very soon on how to convert from one unit to another, so we get better understanding of that. So back to question now. Energy is therefore equal 4.4 multiplied by 10 to the power of minus 19 joules multiplied by 1 electron volt divided by 1.6 multiplied by 10 to the power minus 19. Okay, that should be the case. 10 to the power minus 19 can cancel each other, and joules would also cancel joules here. So I will have that E is 4.4 divided by 1.6 electron volts. So what would that give us? 4.4 divided by 1.6, that should give us 2.75. So E equal 2.75 electron volts. So this would be the corresponding energy to a wavelength of 450 nanometers. So if we have that lambda is 450 nanometer, and the frequency is just going to be, okay, what is the frequency? Come on. So 6.67 multiplied by 10 to the power of 14 Hertz, and the energy is going to be 2.75 electron volts. So this would be the value for that corresponding wavelength. So you can do for every other one, and this is where we're going to stop the class. Thanks for watching, and do have a nice day. If you're yet to subscribe, don't forget to do that. Have a nice day.